Okay, so welcome. I wanted to uh, wanted to get in a little bit early today. Normally, I'll send the Elms invite, like a few minutes before lecture starts, like 5-ish minutes before. We're gonna use the official class time, the like officially allotted class time. Sometimes I might record or I might do the lecture later in the day if I need to for whatever reason. I'll let you know if that's going to be the case. But you can pretty much always count on us the lecture happening during this time. And as you can see, you can ask questions in the live chat there. So um, the later on, maybe in a couple weeks, there may be a few lectures that I record in advance and then post them and tell you, what to watch on a given day. That might happen, like I said, later, like near the end of the month. But typically, this is pretty much going to be the format for all the lectures going forward. So they'll pretty much always take place during this time. The the other thing, so someone was asking, is it 100% online? Yeah, it's 100% online. So immediately following these live streams, these will be pretty much immediately uploaded to the class YouTube channel. So it will be, they won't be nicely organized at first because there's nothing to organize. But as there's more and more videos, I'll start putting them into a playlist so that they're more organized. But because these are the only lectures I'm recording live this session, it'll be easy to find them. They're just going to be the most recent live sessions that I'm doing. If you have already looked at the class YouTube channel, you may have noticed that there's actually like there's like 9-ish, I think it's like 8 or 9 lectures from Math 401 recorded. I haven't looked at those in years. Those were recorded during like the very first COVID semesters, and it was like the last part of the course. So those may become relevant, and I may have you refer to some of those as we get to that material. But for now, these are the main lectures. You can just ignore those. But what I will say, so first of all, in the syllabus, I already mentioned that we're mostly going to be following Justin's notes. This is it's pretty standard for Math 401. Although we're going to supplement it with some other things because Math 401 is kind of it's a fun class in the sense that we have a little bit more flexibility with what we want to cover. So there will be things that aren't covered in those notes, and when I get to that material or when I'm going to cover that material, I will let you know where are the other sources I'm pulling from for whatever it is I'm doing. So that's that. You can read in the syllabus on how like the course breakdown and stuff works, how the format works. So I won't bore you with any of that. There will be periodic office hours, which, like I said, will take place like immediately following lecture, typically. So immediately following lecture, I'll I'll close the stream and upload that lecture, and then I will reopen stream that will, you'll be able to join it via link, but it's not gonna be public on the YouTube channel, so you can come and ask questions during office hours. And if you can't make it to office hours that given day, then you could watch via because it's not going to be public on YouTube. You can, using the Elms link, you could go and watch it. But of course, like not all of you can do that. Like some people actually have to come to office hours to ask the questions, or office hours is going to be pretty boring and just going to be me sitting there and nobody asking questions. So anyway, that's more or less how the course is going to go. So these lectures are a little longer, right, than typical like semester Monday, Wednesday, Friday class. There, instead of 50 minutes, they're like an hour and 20 minutes. So the course, it's summer course, so it's more condensed, right, and we're doing it 5 days a week. So it's a lot more material at a faster pace than usual. But 401 is still pretty relaxed course because we have a lot of flexibility, and maybe you didn't notice this, but if you look at Justin's notes, it turns out that most of the, not all of them, some of them depend on others, but like most of these topics, so it's not even laid out in chapter number. There's just a list of like topics. There's not really necessarily an order to those things. You can essentially do them in any order, and so I am going to be jumping around. There's not going to necessarily be a strict chronological order. You'll be able to piece together a chronological order for the course just based on my lecture numbers, right? So in the description of all the videos, I'll include like the material that I'm doing in that video, so you'll be able to see it in the YouTube description. But basically, these topics can be covered in more or less any order. So so like I might mostly follow the top to bottom way that these are listed, but not always. I will jump around sometimes. So just letting you know that's how this goes. But that's the nice thing about 401 is because we're not in most courses you are rushing towards some end goal, and that end goal builds on everything that came before it. This is not exactly that because there's just a bunch of kind of disjoint and disparate topics that don't necessarily depend on each other. Like I said, a few of them depend on each other, a few of them lead into others, but for the most part, there's a lot of independence between these topics, and so we are going to be jumping around, covering different things. To that end, I think it might be best to start today with review. Now, obviously, I'm not going to try to cram an entire course worth of material, Math 240, linear algebra, into a single lecture. It's not possible, but just kind of a brief overview of these things. So this is not exhaustive. If you want to refer to any of this review material, or you feel like you need to brush up or remind yourself about any of this material, you can look at the review section or the review chapter in Justin's notes. I'm not really going to be following that, but everything I say will be in that basically. So I'm just going to be reviewing these topics off the top of my head as comes from my understanding of linear algebra, but it will match everything in Justin's notes. And like I said, if you want a more exhaustive treatment, anytime these topics come up and you feel like you need to remind yourself what's going on, have a look at the review and that review section in the notes. And otherwise, all of these topics, like linear algebra, people joke and say that linear algebra is the only field of math that's like 100% understood, and that's it's only like a half joke because it is kind of true. Like typically, if whatever situation you're in, whatever thing you're looking at, if you can take the problem you are considering and you can translate it into linear algebra, you're typically very, very happy to do that because it is almost always more beneficial to deal with whatever problem you have in linear algebra land than any other land, because linear algebra land is just, things are far more straightforward. Not necessarily easy, but far more straightforward than in most other fields. So linear algebra is, you're almost always happy when you can turn a problem into a linear algebra problem. So anyway, well, let's just start here. So obviously this is linear algebra, so we are going to be, let's talk about an M by N matrix A. The notation that we'll use here, that I'm sure you have seen frequently, is this. May be written a little bit more expansively. I could tell you exactly where these sub-indices go. So this is read A sub ij. Of course, if there were numbers here, if this is like A sub 1, 2, this would mean that this is the entry in the ith row and jth column of this matrix. This matrix is a rectangular array of entries or numbers. Notice I didn't necessarily say real numbers, although that's likely what you've only had experience with. Turns out that matrices of complex numbers don't behave all too differently. really. And so, what this thing looks like if we write this out. This is A11, A12, A13, and so on out to say A1N. This is A21, A22, and so on out to A2N, all the way down to AM1, AM2, AM3, and so on out to AMN. This is our rectangular array of numbers that make up this matrix. So M is the number of rows, N is the number of columns. Of course, if you have a square matrix, right, mind yourself, square matrix is when the number of rows and columns is the same, right? There are a number of things that there are a number of things we only talk about for square matrices. You may recall this has to do with the determinant, which we'll talk about here in a second. Okay, so this is what a matrix is. Now, I'm not going to refresh your memory on matrix multiplication. You all know how to do that. But if you're rusty on that and it's been a while, you can remind yourself how that works, specifically with matrix times vector. But of course, all of linear algebra ultimately boils down to a single equation, right, which is this one. So matrix times vector is equal to vector ax equals b. Right. So this is kind of like the most important equation in linear algebra. When you first encounter this, when you're doing linear algebra, this comes after you typically have already talked about a system of linear equations. So this equation, of course, has multiple interpretations here. So this is equivalent, of course, to a system of linear equations where if x is we write vectors as column vectors by convention, unless otherwise stated. So this is my vector. How many entries does this need to have? Well, since each row of A has n entries, this needs to have n entries, or this product AX won't make any sense. Right, so this needs to live in Rn. B, however, of course, the resulting thing, I have an m by n matrix times an n by 1. Right, this is an n by 1 column vector. So the result should be an m by 1 matrix. So B should be in Rm. And, another way of writing that is to say this vector B contains m entries. And this is because A has m rows, right? Okay. So already you might recall that you can view this equation as a linear transformation, T, that goes from Rn to Rm. Right? That is, it takes a vector. So the linear transformation T, you could say, it takes in a vector x in Rn and it multiplies it by the matrix A. This is called the standard matrix for that linear transformation. Right? If this is the case, if T can be written like this. This defines a linear transformation from Rn to Rm, so it takes a vector in Rn, sends it to Rm. So this is one of those interpretations that I wasn't even going to include here, but I might as well write it now. Okay, so what else? What's another interpretation here? Of course, the first thing you start out with typically in 240 is a discussion of systems of linear equations, right? That's typically the very first starting point. So the first thing you see in a 240 course, before you've even talked about matrices or matrix multiplication, is systems of linear equations. So this is, we know, equivalent to a system of linear equations. That system of linear equations I can just read off from all of these things. So if my matrix A is here, here's my solution vector x, here's my right-hand side vector b. what can I say here? Well, I can say this A, I can call the coefficient matrix for the system I'm about to write down. And if I unpack, in terms of matrix multiplication, if I unpack what this equation is, I literally get this thing I'm about to write in brackets here. So this is a11 times x1 plus a12 times x2, and so on, all the way out to a1n times xn is equal to b sub 1. For the second equation, I would get a21, I'd be at basically the second row, right, of a here is going to be transposed and dotting this solution vector. That's how matrix multiplication works for matrix times vector, right? X1 plus a22 times x sub 2, and so on all the way to a 2n times x sub n, and that is equal to b sub 2. And so on in that fashion until I've written out all of these. There are m such equations, so this would be a m1 times x1 plus a m2 times x2, and so on all the way to a mn times xn, and that's b sub m. So we get m equations and n unknowns. Right? This is how this equivalence works. So it is clear, if you know how matrix multiplication works, it is clear why these two things are really the same object, right? So seeking out solution vectors x that solve this matrix equation ax equals b is the same as seeking out solutions to this system of linear equations, right? And this is typically the starting point of when you go beyond the systems of linear equations and you move into matrix algebra or linear algebra, right? So that's typically what happens. What happens is you start with this, you say, wow, systems of linear equations, those are those are important for a variety of problems, and I want to be able to solve those as in efficient a way as possible. Well, it turns out that writing them in this form is very nice for a lot of reasons, right? It allows me to immediately write out my algorithm for solving linear equations, the algorithm for putting a matrix into reduced row echelon form, which I'm not going to go over, but putting a matrix into, I'm not going to review that. You can look at the notes. But putting a matrix into reduced row echelon form, or depending on the textbook you use, row echelon form, or reduced echelon, sorry, not row. They get rid of the row, right? If you're using MATLAB, right, it's still RREF is still the command. But in textbooks, they eliminate the word row in this, so it will be called reduced echelon form and echelon form, respectively. Those will be the things. But regardless of what you call it, this is the same thing. This algorithm, this Gaussian elimination thing that puts a matrix into reduced row echelon form, that is what you start out doing, solving this. Putting it in this form is nice for a variety of reasons, and then we see that actually what actually matters here is the algebra that you're doing on the matrix itself. And then you move beyond, right? You detach yourself from linear systems or systems of linear equations, and then you start talking directly about algebra of matrices. So anyway, one more interpretation here, just to remind you. There's the other interpretation that both of those, I'm going to rewrite ax equals b here, but ax equals b is also equivalent to another formulation using the same notation from the last sheet. This is also equivalent to the following, which is writing. So there's an alternative way of writing this that sometimes is very convenient for our purposes, for defining things and for keeping track of things. It's to think about writing this as okay, right? If you had to boil down, what is a matrix? You're probably going to say it's a rectangular array of numbers. Okay. But, what's maybe an even nicer way to describe what a matrix is? A matrix is a vector of vectors, right? It's a vector where in each slot, instead of having a scalar, right, instead of having a scalar component in each slot, you have a vector in that slot. So it is convenient to write this in a rectangular fashion because you have the vector written horizontally, with its components as the slots, and then you slot into it vectors written vertically to save yourself space, right? So it's a vector of vectors is essentially what a matrix is. An array of arrays, if you really like that terminology. That's what is going on with a matrix. So in that way, it is, maybe suggested just from that what I could do is I could view each of these itself as a column vector. I'll call this A1, which is the first column of matrix A. This is A2, and so on all the way out to AN, so that I can write this as the matrix whose columns are these vectors indicated. Okay, so sometimes it is convenient to write a matrix in this form. Okay. And then you can see that if we have written it in this form, looking down here in this system of equations, you see that, okay, we have here is my first column vector times the component x1. Here's my second column vector times the component x2, and so on. Here's my nth column vector times x sub n. And so I can, and of course here's my column of the right-hand side entry, so this is my vector b. I can see how this, being equivalent to this directly is equivalent to a vector equation that looks like this. And maybe I could even write I'll write the scalar thing first, right? So now, when you're reading notes or a textbook, they can do boldface for vectors. I can't with a pen. And so what I will do instead is put this arrow or bar or whatever over it. If you want to use a hat, that's fine too, just to indicate that it is a vector. Okay. So I get the following vector equation, where the x sub i's are scalars. They're the components of the solution vector. Right, so the x sub I are scalars, and the a sub I are column vectors of A, right? I'll put vectors in parentheses there. They're the columns of A, and I'm treating them as vectors, right, in their own right. So this is what I get. This is a vector equation now. When you have a vector equation written like this, of course, you might recall that this left-hand side has a name. You're probably already screaming it into your screen, maybe. What you call this. You can type it in the chat if you want, but what do you call this left-hand side of this equation when you have scalars times vectors and then you add them all up? This is called a linear combination, right? So this is a linear combination of the vectors A1 to AN. So you have arrived at the end point of all these equivalencies between the different things, the matrix equation, the system of linear equations, this vector equation. And this means that there's like a list of 15 different ways or more that I could ask you to solve one of these things. So I could just put a system of linear equations in front of you and say, solve this, right? Like, solve this system. That's one way I could ask. Or I could put the matrix equation in front of you and ask you to solve that. Or I could ask a question like, is B a linear combination of the columns of A? And asking that question is the same as asking for a solution to this vector equation. It's the same as asking for a solution to this system of linear equations. It's the same as asking for a solution to this matrix equation. This is not the only way I could phrase this, obviously, but this is just showing you that all of these things are equivalent, and these are really the same way of asking these things. So I heard my cat meowing, so I'm going to feed her so that she doesn't freak out during the lecture. Okay, cat is fed. All right. So, all right. So this is just another way of asking for a solution to one of these three equivalent things. Talking about linear combinations, of course, it's not apparent yet because we haven't mentioned vector spaces. I'm going to mention them briefly here in a little bit, but the this this question is B a linear combination of the columns of A. Talking about linear combinations, what is the kind of importance of a linear combination? Linear combinations are the building blocks of all these vector spaces, right? And we know that vector spaces are the abstract versions of the most common linear algebra spaces we talk about, which are the Rn, right? So Rn is our most commonly discussed vector space, and in a sense, it's kind of, one of the only ones. It's not exactly the only one. There are infinite dimensional vector spaces, as you might recall. So if you want to know an example of an infinite dimensional vector space, consider the vector space of all continuously differentiable functions on the interval 0 to 1, where vector addition is just pointwise sum of functions, and scalar multiplication is pointwise scalar multiplication of functions. Like that is an infinite dimensional vector space. Involving function spaces is a good way to pass to an infinite dimensional vector space. So the vector space of all polynomials, right, of any degree, right, in some variable t, things like that. Like those are infinite dimensional vector spaces. So not every vector space is Rn, but any finite dimensional vector space is in fact just some copy of Rn, right? You might remember discussions of isomorphism from linear algebra from 240. If vector spaces are isomorphic, they are really the same. But I'll get to that. I'll get ahead of myself here. So linear combinations are like the building blocks of all vector spaces. So questions about linear combinations, not surprising that they are important in this discussion, because these are like fundamental objects in some way. Okay. Now, we have discussed various equations, right? We've discussed matrix equation AX equals B, linear system of equations, vector equation like this, and we're wanting to solve them. So wanting to solve them, it's probably important to know how many solutions we can expect. And again, you can put it in the chat, but we know that this depends. Right? So the question is, how many solutions does this vector equation have? Well, the question is B a linear combination of the columns of A? It might not be, right? That's possible. So we could have 0. Okay? The next question is it, re-asking this, is it a linear combination of the columns of A? If it is, it's possible that there's not only one way to do this. Right? In fact, well, there's many things you could say here about whether or not this is going to be unique, but we know that AX equals B, right, can have a unique solution. It can also have infinitely many solutions. So for any of these things, right, when you are considering, like at its core, when you are considering the equation AX equals B, there are 3 options. This is a recurring theme, right? No solution. Unique, exactly one solution. But if you're not in these cases, it's not possible to have like exactly 7 solutions. That's not a thing. You either have no solution, exactly one solution, or infinitely many solutions. So this is what is going on here. Okay, and this is recurring theme. This is always something you have to consider no matter what size your matrix is, even if it's square, these options all can occur. Okay, so so this can always happen. Um, so that is something to consider. There's no way to, you need to know additional information to rule out any of these things. Okay. Now, here's the thing, right? Let's suppose for a second that we are in the case that we have a square matrix. That is a matrix that has the same number of rows and columns here. Okay. If we are in this case, the question is, does this simplify anything? Does this allow us to simplify and say, oh, we're always in either, 1, 2, or 3? And the answer is, it doesn't allow us to simplify in terms of that. All these three things can still happen, but it does allow us to neatly tie up which of these things happen in kind of the following way here. So first of all, I want to move to, I always, when I'm teaching Math 240 or Math 461, I always tell students that, row reducing a matrix is the thing, that you have to have the most practice with, because basically every question you ask in the course has to do with row reducing a matrix. And the only exception to that, essentially, is this next thing we're going to talk about, which is a thing that is only defined for square matrices, and that is the determinant. Okay. Now, I'm not going to go over the determinant here. If you need to refresh your memory about how it's an alternating sum, it's this weird alternating sum. You can use cofactor expansion. Computationally, that is not a great way of doing it. It's a great way of doing it by hand, kind of understanding what's going on, but computationally, cofactor expansion is pretty awful. It really blows up. The number of operations required goes crazy pretty quickly. You can tell that immediately when you think about what it means, right? So computing using cofactor expansion, I'll write it out here. But like I said, I'm not going to do that because the point of this course is not going to be doing long determinant calculations by hand. So cofactor expansion, right? To compute the determinant of a 3 by 3 matrix, you have to compute 3 2 by 2 determinants. And to compute the determinant of a 4 by 4 matrix, you would need to compute 4 3 by 3 determinants. You see where I'm going with this. To compute the matrix, or the determinant of a, well, I should say it again. For a 4 by 4 matrix, you would have to compute 4 3 by 3 determinants, each of which is 3 2 by 2 determinants. So then to compute the determinant of a 5 by 5, you would have to compute 5 4 by 4 determinants, each of which is 4 3 by 3 determinants, each of which is 3 2 by 2 determinants. You see that computationally this is awful. So there are other methods, there are other things employed when a determinant needs to be computed numerically. The main point is that the computation of the determinant determines whether or not the matrix A is invertible, right? And so recall, right, if A inverse exists, this is a thing that can only happen when you have a square matrix, so that's one thing to note. But if A inverse exists, then if we multiply both sides of AX equals B by A inverse, matrix multiplication is associative. So that this is the identity matrix, the n by n identity matrix, which we know multiplies any vector and gives you back the vector itself. So this tells you that, oh, actually, the solution is unique in this case. It always has to be this thing. So the solution vector I seek is just the inverse times the right-hand side vector. Okay? So this answers a question about what sort of thing I can expect. Okay? Whether I can expect, one solution or some other case. Well, if A is invertible, in fact, I get exactly one solution. So then the other cases can only happen when A inverse does not exist. So the point is, this is called the invertible matrix theorem. Now you might recall that the invertible matrix theorem will just be conservative here and say that this has like 20 parts. Okay, but it actually has more than that. You might recall, typically, the way instructors handle this is the first version of the invertible matrix theorem that you see has maybe like 10 parts or something, and then as the semester goes on and you learn more things, you add parts to it until you get to like part S or whatever. And so what is the invertible matrix theorem? The invertible matrix theorem is essentially a thing that tells you how nice invertible matrices are, but the main part of this will say, like, basically it's a list of the following are equivalent. TFAE, you'll see that some in this course. The following are equivalent. That's what this means. I'm not going to list all of these. You can look up statements of these things, but basically, I'm just going to list like the main thing, which is determinant of A being non-zero. This happens exactly when A inverse exists. Okay, and then you get a bunch of nice things. So you know a bunch of nice things about A once you know that its inverse exists. You know that its columns are linearly independent, right? So this is a good place to bring up linear independence since it relates to those linear combinations we talked about. So linear independence. What does this mean? This is, one of the core this is like one of the core things, one of the core notions in linear algebra is the notion of linear independence. What does linear independence mean? It means if whenever for, this is a terrible way of me writing this, but just bear with me. If whenever for some set of vectors, we'll say v1, v2, and so on. I'm not even going to specify whether they're in a vector space or are in or whatever. It's fine. Either way, you get the point. So we'll say v1 to vk. If whenever for some set of vectors v1 to vk we have for scalars c sub I the following: c1 v1 plus c2 v2 and so on out to ck vk. When we add those together, when we form that linear combination with those scalars c1 to ck, and we get the zero vector, you can either treat this as the zero vector in Rn, which is just the vector of all zeros, or the zero vector object in a vector space. In that case, the scalar c sub I would come from the field that vector space is over. Okay, so usually the reals, but it doesn't matter here. We can still define this either way. If whenever you have a linear combination of a set of vectors being equal to 0, and if those vectors are going to be linearly independent, then all of these scalars must be 0. In this case, we would say, I know that I've kind of awkwardly stated it here. In this case, we would say that this set of vectors is linearly independent. So remember, in the event of, or whenever you're talking about linear independence, it's not a property that a vector can have. It's a property that a set of vectors can have. So it doesn't really make sense to say that a vector is linearly independent. It's a thing you apply to a set of vectors. So a set of vectors can be linearly independent. Single vector, not so much really. So anyway, this is the notion of linear independence. Again, there's so many. I could spend multiple lectures just talking about linear independence, but you've already seen that. You've already seen that previously. And if you are hazy on any of that, of course, have a look at the review section in Justin's notes. But one of the things the invertible matrix theorem allows you to say is, okay, if A inverse exists, then all of its columns, all the columns of A are linearly independent, right? So, on the other hand, linear dependence means that you can, in fact, have this relationship between the vectors that would be called a linear dependence relationship, and these C sub i's are called the weights in this linear combination. These are called the weights. Okay. So again, it's not possible for me to cover all of Math 240 like this. So, if this seems fast, well, it is because, this is a brief review of all these topics. Okay. Now, very quickly, a vector space. I'm not going to list the vector space axioms, but what is a vector space? It is a set, V. It has a list of axioms that specify certain properties it has to have, but one thing that is specified, one of the axioms, is that this is not allowed to be empty, so it has to have at least one vector. The vector that it has to have is the zero vector. It might only have the zero vector. In that case, it would just be called the zero vector space. But typically it's going to have more. The canonical example of a vector space is Rn. And so when you see the vector space axioms, you're immediately going to note that all those axioms are true in Rn. And that's by design. Rn is being used to model the abstract vector space. Okay. So what is the thing here? What are the two things that make up a vector space? A vector space is a set together with two operations. One we'll call plus, and the other, I don't want to write a dot here and make you think that it's a dot product I'm talking about. So I'm going to write it out. I'll say scalar multiplication. So you have two operations, vector addition and scalar multiplication. So for instance, what's an example? If I take my vector space to be Rn, then my vector addition would be, so I'm only going to do this once, but when I write a vector and you know where it lives, you can assume that it has similar notation here so that I don't have to rewrite this every time. So when I write the letter U as a vector, I'm writing all of its components also using the letter U just without a bar over them to show you that those are the scalar components. Okay, there's V. U plus V, of course, is this thing. It's the just component-wise addition of each of those things. You might say, well, okay, yeah, that's how adding vectors is defined, right? And this is where I get the parallelogram rule from when I'm doing this. But the definition of vector space has in it an operation called vector addition, and then part of the axioms are telling you how vector addition behaves. This satisfies all those axioms. That's what makes this a vector space. The other thing is if I take a scalar C and R, then of course scalar multiplying a vector is defined this way. Maybe rather than writing equals here to show you that I'm defining these things, I'll write this. You'll frequently see me do that. That means that the symbol on the left is defined to be that thing on the right. The way to think about this is, like I said, vector space has a list of axioms. Those axioms tell you that it's a set that has two operations. vector addition and scalar multiplication. Those can be defined however you want. They just need to satisfy that list of axioms. So if I define them this way for the set Rn that we know, then it turns Rn into a vector space, what's called a vector space. Now, you might say, what is the point of any of this, right? Like, is there a point in using vector space stuff if you just told me that all finite dimensional vector spaces are the same essentially? They're all just some of the same dimension, are the same. And the answer is, here's like canonical example. Let's do let V be the set of up to degree 2 polynomials in the variable t. And so then what does that look like? That is like a set, we're using set builder notation here, that's like a set of objects that looks like this. It's like a0 plus a1t plus a2t squared, right? Such that I didn't specify this, but I guess I should say with real coefficients. So with real coefficients, so a0, a1, and a2 are real numbers. So it's the set of all polynomials that look like this, right? Up to degree 2, so I'm not allowed a t cubed term here. Set of polynomials up to degree 2 with real coefficients. So a0, a1, and a2 are all in R here. What is my plus going to be? My plus is going to be pointwise addition of functions. So for instance, if we had the polynomial a0 plus a1t plus a2t, or a2t squared, sorry, we'll call this vector A plus the vector B, which is b0 plus b1t plus b2t squared. That's my vector B. I could, since I'm calling that pointwise addition of functions, I just add them like I do anything else, and I group the terms. So this would be a0 plus b0 plus a1 plus b1 t plus a2 plus b2 t squared. Okay, this is my new object. Now you might say, wait, this isn't a vector, this is a polynomial. Well, in a vector space, the objects that make up the vector space are just called vectors. That's what they're called. So these are vectors in this vector space. Now you might say, is this a vector space yet? We don't technically know. That's true, but if you use this, if you say this is my pointwise addition of functions, and what is my scalar multiplication now? So let's do scalar mult. So if I have a scalar c that's a real number, how about c times the vector a? That is c times this polynomial a0 plus a1t plus a2t squared. What I mean by pointwise multiplication is I just distribute this thing, so this would be c a0 plus c a1t plus c a2t squared. And it turns out that that V is a vector space. And you probably don't have to think too hard to realize what vector space this is. Right? So what vector space is this? I will give you a few seconds in the chat. I'm going to refill my water, but I'll give you a few seconds to tell me what vector space this is. You might say, what am I even asking here? I mean, it's the vector space that's up to degree 2 polynomials, real coefficients, and variable t. No, I mean, this is equivalent to, well, not equivalent, it is the same vector space as a vector space you know. Let's see. Did anybody say what it is. No, nobody said. Well, um, actually, V is isomorphic to R3. This is actually just the same vector space as R3. How can you tell? Well, these T's you can think of as just placeholders, but is this substantially different than if I wrote this as the set of vectors that look like this? Such that A0, A1, and A2 are real numbers? Well, no. And in fact, look at what vector addition is then. You add the components component-wise, just like you do in R3. Scalar multiplication, you scale component-wise, just like you did in R3. Right, so this is literally the same thing. This symbol means is isomorphic to. Depending on your instructor for Math 240, how much they talked about isomorphism. If two vector spaces are isomorphic, they are the same as vector spaces. So in the realm of vector spaces, they are identical. It is like having congruent triangles, right? You might say, well, why do you use a weird word, right? Isomorphics from the Greek. Iso means same, morph means type, so it's same type. Why do you use that instead? Well, it's the same reason that you use congruent for triangles instead of saying equal, because equal's too restrictive, right? Like the usual thing I draw is like, okay, here's a triangle, here's the same triangle. But you would fight me and say it's not the same triangle because this triangle's here and this triangle's over there. So they clearly can't be the same because this one's there and this one's there. Well, okay, right? That's true because technically to be literally the same triangle, they would need to like match up, point for point, vertex to vertex. Like everything would have to be like perfectly aligned. It'd have to literally be the same. But that's way too restrictive. We want to be able to say that these two things are the same if you could do the Euclid thing and say if you could apply rigid motions of the plane to move one of these onto the other, that's just a fancier way of saying that they're congruent, right? So if you think about putting like translucent paper on it and tracing this, you could apply rotations, reflections, and translations to move this perfectly onto that thing so that it could be lined up. This is how you talk about congruent triangles. This is essentially what you're doing with vector spaces. It is, when you say two vector spaces are isomorphic, it means that one is just a relabeling of the other. Now you could ask the question, well, wait a minute, like, then what's the point of doing any of this? If this is the same as R3, why not just work with R3? Well, notice what this would allow you to do. Now, I don't know what question you're considering about polynomials of up to degree 2, but the point is that you took a thing that lived in a kind of a different land, polynomials of up to degree 2, and you moved it into linear algebra land by putting a linear algebra structure on it, putting the structure of a vector space on it. And so you took me asking you questions about up to degree 2 polynomials, maybe off the top of your head you don't think of that as a vector space or a linear algebra type question, but it might be, right? So that's the point. The point is being able to understand the underlying structure, in this case vector space structure, even when it might not be apparent, is important. That's what allows you to move a problem from the realm of, say, economics or game theory or graph theory or any of these things that we're going to talk about. To take that and move it into the realm of linear algebra, you have to recognize the underlying linear algebra structure, which is vector space structure. So what is linear algebra? It's the algebra you do in vector spaces. Like vector spaces are the like fundamental object in linear algebra. They're the space that you are in when you are doing linear algebra things. So that means that in this course, they are the universe that we live in when it comes to all these computations that we're going to be doing, all these linear algebra things. Okay, so what else do I want to talk about? Maybe it's a good time to go ahead and talk just a tiny little bit about orthogonality. I'm not going to spend too much time on it now, but we will discuss it more when we need to. There is a structure on vector spaces that is not technically included in the base structure. And you, if I phrase it in a different way, maybe it's more obvious of what we're missing. So in vector spaces, you can talk about adding two vectors. You can talk about scaling vectors. That leads to a lot of things you can think about. But one thing it doesn't lead to on its own is the notion of, well, what, if I ask you, if we go back to like Calc 3 or physics or whatever thing you're doing, engineering, whatever thing you're doing, and I ask you to describe what a vector is, you might say a vector is an arrow, and I'd say, okay, well, what does that arrow indicate? Right? Some of you might say, well, a vector is a point and a point's a vector. That's fine too. But if you think of a vector being data, right, that is like a direction and a magnitude. Magnitude, length of vector. Well, we haven't said anything about length of a vector, and the reason why is because we don't have a way to talk about it without additional structure that has to be added. That additional structure is called an inner product on a vector space. I'm not going to write out the generic, you can look up the inner product axioms on a vector space when you have an inner product present. I'm not going to write those out because for our purposes they're not as important. When we need to refer to them explicitly, I might bring them up. But the main thing is to know that there is an example of an inner product on a vector space. Take the vector space to be Rn with the usual vector operations, and take this inner product. So the inner product pairs two vectors in your vector space. So it takes a vector and a vector in your vector space, and it spits out a real number, a scalar. If you're talking about a vector space over the reals, here it should take two vectors, pair them up, and assign to that pairing a real number. And part of the axioms of the inner product is you can pull scalars out of it when it doesn't matter what order you pair them in. So U paired with V, V paired with U is the same thing. That's symmetry. You can pull scalars through them. I'm basically stating all the axioms anyway, even though I said I wouldn't. I can't help myself. I'm sorry. Anyway, this assignment, right? If we take this pairing, in this case, to be the dot product that we are all familiar with, then that dot product, the algebraic rules of the dot product satisfy the inner product axioms. It's an inner product on your vector space. And the immediate application, of course, is that the dot product we know from Calc 3 or from 240, that this is a thing that that specifies whether or not two vectors are orthogonal. That is just a higher dimensional analog of being perpendicular, of course. So these two vectors, if you dot them together and you get 0, that happens if and only if they are orthogonal. They are perpendicular. So maybe I'll write out. Now, there's a lot of things that orthogonality is nice for. So in order to talk about maybe the thing that it is nicest for, I need to talk about linear independence again in the form of a basis for a vector space, which is that allows us to put coordinates on a vector space. And talking about orthogonality and how nice it is for coordinates, that's where I'm going with this. So I'll be back to the dot product and orthogonality and why I mentioned length earlier here in a second. But basically, what is a basis for a vector space? I mean, informally, if we're just saying like what's the most important thing to know about a basis for a vector space, it's most efficient So most efficient set of building blocks for a vector space. If we're being a little bit less informal, so more formal, it's a most efficient spanning set. Using the terminology of 240 here to talk about what is a span of a set of vectors. It's the set of all linear combinations of those vectors. And so just recall a span of a list of vectors is set of all linear combinations of those vectors. So if I write it in set builder notation, it is the set, an object in here looks like this. Such that these CIs are all real numbers, or just some scalar. So it's the set of all such things that look like this, all set of all linear combinations. So when I said earlier that linear combinations are like the fundamental object in vector spaces, this is what I meant. Because as we'll see, you can find a set of these in any vector space such that the span of those vectors is equal to the vector space. So the set of all linear combinations is equal to the vector space, meaning any vector in the vector space can be written as a linear combination of those vectors. And you can do this in a way that this spanning set is as efficient as possible. It has the least amount of vectors as possible. And if that is the case, we call it a basis. So what are the things that we need here? We need two important things: the notion of linear combination and span, and the notion of linear independence. So a set, we'll call it B, which is a set of vectors v1 to vk, is called a basis for a vector space V if two things are true. One, the span of that set of vectors is equal to V, and two, that set of vectors is linearly independent. Condition one ensures that those vectors fill out the vector space when you consider their span, that they span the vector space. That's the terminology you use. So that every vector in the vector space can be written as a linear combination of those vectors. But of course, there's many ways you could do that. You could throw in vectors that are extra, that you don't need. They're superfluous. They don't add anything. So in order to ensure that we have the most efficient such set, we have this requirement that they are linearly independent. You might recall from 240, if you're in this situation, if you add in another vector here, they won't be linearly independent anymore in this scenario. If you take away a vector, they will not span the vector space anymore. So if you start with a linearly independent set and you take away one of those vectors, you now will no longer span the same space. I didn't go over a subspace before, but one of the most important examples of a vector space other than Rn is for any vector space, if you have a subset of that vector space that still satisfies all of the vector space axioms, you had a couple things to check. You needed to check that basically it was closed under scalar multiplication and vector addition. That's what you had to check. That includes that it contains a zero vector. But you often check that separately because it comes up very frequently. But subspaces are just subsets of vector spaces that are vector spaces in their own right. They inherit the vector space structure from the ambient space. So for instance, taking a span of a list of vectors, any list of vectors is always a subspace of the vector space in question. You can throw in all the vectors in the vector space and always get a spanning set, but that's too big. You need less than that, and so this ensures that we get that. And so if this is the case, if this is a finite list and this is a basis, this gives us the notion of the dimension of V is K. Because while every vector space has a basis, that's a that's a fact we get from the axiom of choice. We're not going to debate that. So every vector space has a basis. But also, there's typically infinitely many bases for a vector space you can come up with. Vector spaces do not have unique bases. These bases are not unique. There are preferred bases, like there's the standard basis for Rn that I'll write out here in a second. But the point that is determined is the number of vectors in a basis is always the same. So while the basis, like the actual bases might change, the number of vectors in a basis will never change. And that number is what we call the dimension of the vector space. You might remember all this stuff. So for instance, here's an example. So here's script B. Here's my list of vectors. And here's, we'll say script C. Now it turns out both of these are bases for R3. So B and C are bases for R3. Now they're clearly different bases because they have different vectors in them. Okay, but notice that they both have three vectors, right? And R3 is in fact three-dimensional because of these three vectors. Don't get focused on the number of components. That doesn't have anything to do with dimension. What dimension has to do with is counting the number of vectors in a basis, right? That's what dimension has to do with. Now, you might say, well, okay, I have multiple bases, then how do I know which one to use? So the bases are used to put coordinates on vector spaces. And I'm not going to go into coordinates and coordinate changes and all that, but the point is that there is typically a preferred basis. For instance, this is even called the standard basis usually, and the notation we use for it is this. So the E sub I is like the ith standard basis vector in Rn. It's zeros everywhere except in the ith slot it has a 1. So these are, another way you could view this is these are the column vectors of the associated identity matrix, right, for that size. So in this case, these are the columns of the 3 by 3 identity matrix. So what is it that's so nice about this? This is an orthogonal set. It's also orthonormal, which I'll talk about in a second. That's not as important. What's more important here is that this is an orthogonal set. It's an orthogonal set because if I dot any of these vectors with any of the other vectors in this set, I get 0. They are orthogonal. For a variety of reasons, I don't have time to go into all of them, but for a variety of reasons, having an orthogonal basis is really, really nice. In terms of coordinates, it essentially gives you these unique coordinate expressions, a very quick way of finding out, being able to compute weights in linear combinations. Like there's all kinds of benefits to this. So it's not, it is not for no reason that this is called the standard basis, and this is like a preferred basis in a lot of ways. But also, the lengths of all these vectors is 1. But how do I compute the length of a vector? Well, the length of a vector, which you might write it like this, for instance. Maybe I'll use v here since I've been using v for the previous statements. So what is the length of a vector? It is, if you like, you can think about it as defined like this. It is the square root of the vector paired with itself using that inner product on the vector space, if you have one. For the dot product, this would be the square root of v dotted with itself. If v is in R3, I'll just write it in Rn. Why not? This would be the square root of v1 squared plus v2 squared, and so on, out to vn squared. Sorry, not k. to be squared. Okay. So the dot product not only gives us a way of describing orthogonality, it also allows us to compute length, right? That's one of the main purposes of this. And saying that this is orthonormal means it's an orthogonal set, and also each of those is a unit vector. Each of those has length 1. Okay. Real quick, and we'll kind of finish this overall review. I know it's been pretty quick, and like I said, I might spend like maybe 10 minutes the next lecture like really closing it out. But let's go over one more thing which I haven't mentioned yet, which is one other instance in which straight row reduction is not the thing you're doing, but it does involve a determinant, so that's maybe not surprising. Eigenvalues and eigenvectors. Okay, so by definition, what is an eigenvalue? An eigenvalue is a number, we'll call it lambda. Because you already know that this number can in fact be a complex number, it can be an imaginary number. That's why I'm very careful and I call it a number and not a real number. These eigenvalues do not have to be real. There are matrices that have only real entries that have complex eigenvalues. That's how it works. Because, of course, there's a polynomial involved, and whenever you're talking about roots of a polynomial, you always got complex numbers as a possibility there. So anyway, what is an eigenvalue lambda and an eigenvector v? These come in what are called eigenpairs. You can't really talk about them separately. You can talk about eigenvalues on their own, but talking about an eigenvector on its own is not really a thing. It's always relative to some eigenvalue. What is this? It is a number such that on a corresponding eigenvector v, multiplication of that vector v by the matrix A acts like scalar multiplication. We would say that lambda is an eigenvalue for the matrix A. These matrices, for a reason that will be apparent very quickly, these need to be square matrices, or this doesn't really make sense. So lambda is an eigenvalue for a matrix A, and V is its corresponding eigenvector. So it's an eigenvector corresponding to the eigenvalue lambda. Looks like this. So A acts like scalar multiplication on V. And the scalar you're multiplying by is the eigenvalue itself, lambda. This leads to, very quickly, now I'm going to do this. I'm going to say AV minus lambda V is equal to the 0 vector. I just moved lambda V to both sides. Here you may be very tempted to say, okay, I can factor the V now, but not really, right? You can't, like if the thing you're trying to do here is write A minus lambda times V is equal to 0, that's doomed to failure because you might notice that A minus lambda is a matrix minus a scalar, and that doesn't make any sense. So this doesn't make any sense, but if I add in an identity matrix of the same size here, now this suddenly makes sense. And now solving this equation for either lambda or v, whatever's going on here, amounts to a question about this, what is called a homogeneous matrix equation, because the right-hand side is the 0 vector. The thing about a homogeneous equation is we know that it always has at least the 0 vector solution. Okay, so v equals 0 is always a solution. We're going to toss that out. We don't count 0 as an eigenvector for any matrix because it would always be an eigenvector, and it would screw things up. It'd screw up all the statements you want to make. So the 0 vector is never considered an eigenvector. But what do I do? Well, I say, okay, the only way that this has a solution that's not the trivial solution, that's not just the 0 solution, is if this this matrix is not invertible. If that matrix is invertible, then the only solution it has is the zero solution. So we want that matrix, A minus lambda I, to not be invertible, which means we want what? If we want it to not be invertible, we want its determinant to be 0. So we want the determinant of A minus lambda I to be 0. And of course, you recognize immediately this is the thing that allows you to find eigenvalues here. This is called the characteristic polynomial of a matrix A. And this is how it's computed. Maybe you saw this reverse so that it was lambda I minus A whenever your instructor did it. There's no difference because, well, okay, technically the difference is there's a minus 1 to the n factor, right? Like if you did it the other way, if you wrote it as a determinant of lambda I minus A, technically there would be an extra minus 1 to the n factor here. But you're finding roots, so who cares, right? You're finding roots of this thing, so you don't care. So I'm just going to write it like this, but just know that these are the same thing. For conceptual things, this might factor in, but otherwise you don't have to worry about this. So there's my characteristic polynomial. This is a polynomial. It's a polynomial of degree n, where n is the size of A. So for 2 by 2s, it's a quadratic. For 3 by 3s, it's a cubic. For 4 by 4s, it's a quartic, and so on. So this means that for any matrix bigger than a 2 by 2, you're going to have to find the roots of a cubic, a quartic, whatever, a degree n polynomial. Okay, and those roots are going to be the eigenvalues. Finding the eigenvectors, I'm not going to go over that. That's solving linear systems. You all know how to do that. And if you are rusty on that, refer to the review section in the notes. And you can get some practice on those things. Of course, what is the purpose of this? The purpose, going back to this original formulation, is that A acts like scalar multiplication on V. The eigenvalues of a matrix essentially allow you to completely predict the behavior of any system or anything you are modeling that can be modeled through iterative matrix multiplication. So let me give you an example. So let's say we have some process that we're trying to model. Okay, and we have our model matrix A. We'll call it a model matrix. There's a variety of things where this could arise, and in that context it might have a very specific name. But in our context, we're just going to call it a model matrix. So whatever thing we're trying to describe, A is our model matrix. Maybe we obtained it empirically from data collected in a variety of experiments. However this was obtained, we have this model matrix. So typically this is going to be a gigantic matrix. It's going to be a huge thing. But it's some square model matrix. And then we have an initial data vector, okay, that I'll call x naught. So initial vector. Okay. And the point is that going to the next time step. So this initial vector, this is our initial data. This is our 0th time step. So then what about the first time step? Well, the first time step we define, this is what the model matrix does. The first time step for this process is defined to be the model matrix times this initial data vector. Okay? So this is my first time step. Well, then what's my second time step? To get to the next time step at any step in this process, I simply multiply by the matrix A again. So the second time step is gotten by iterating this by multiplying by A again. So I multiply x1 by A, but x1 itself is A times x naught. So writing this all in terms of x naught, this would be, sorry, I'll write it like this. This is A times x naught. Associating the matrix multiplication, this is A times A, or A squared times x naught. Okay, let's keep going here. What about the kth time step? This would be x sub k. This would be a times x sub k minus 1, so a times the previous time step. But then this is going to be a times a times a times and so on, all the way out to a times x naught. There's going to be k such things here. So this is going to be a to the k times the initial vector. So two things here. This process I can model, and to understand the behavior at any time step, all I need is the initial vector. I don't need anything else, just the initial vector, and then powers of k. But the thing is that a to the k is nasty, right? This is, just try it, right? Try to do it even for a squared or a cubed. It's not what you think, right? It's certainly not the easy, like you can't just raise all of the components of the matrix to that power. That's not what this is. If you actually write it, just do it, right? A squared is a times a. Pick your favorite 3x3 matrix and do that, and you'll see that there's no good way to do this. There's no good thing that comes out of this. And so eigenvalues make this super easy. So eigenvalues allow me to fully understand this thing. And I will stop here for today, and I'll pick back up and kind of finish some of this review, and then we'll start on some of these actual topics tomorrow from the notes. But anyway, that is the first lecture under our belts, and I will see you all here same time tomorrow. If you have any questions, email me and all that. Your first homework will be posted sometime later in the week. Obviously, any of that stuff comes through Elm, so you will get an Elms announcement for that thing, when all that's due, all those things. Next office hours, I'll announce that also in an Elms announcement, so just be on the lookout for it. But anyway, that is all for today, so I will see you all tomorrow.